Hello everybody, my name is Luka Rogelj and I come from Faculty of Mathematics and Physics, University of Ljubljana, Slovenia. Today I will present a poster with the title Intensity Correction of Hyperspectral Images with Three-Dimensional Profilometry Data. Firstly, I would like to emphasize that when imaging samples with hyperspectral imaging, there are also other things besides bulk properties that can affect spectral information. Among them, there are thickness, smoothness, shape, and curvature of the sample. So, when we are imaging curved surfaces, some artifacts appear on inclined area which can significantly affect the spectral data and contribute to inaccurate optical parameters. In our poster, we present an optical method for correction of images using three-dimensional laser profilometry. Firstly, I would like to show you which scanning system that we used in our study. We use in-house built push-broom hyperspectral imaging system. Push-broom means it captures one spectral and one spatial dimension at a time, therefore scanning is necessary in other spatial dimension. The system is covering wavelengths from 400 to 1000 nanometers with resolution of 1 nanometers. On this figure, you can see the photo of our system and the schematics of our system. The system is built out of translational stages, camera for hyperspectral imaging, objective, imaging spectrograph, and polarizer. We used polarizers to get rid of specular reflection. To detect three-dimensional shape of the sample, three-dimensional laser profilometry is used. As you can see on the image here, if we illuminate curved surface with the laser line becomes distorted. With triangulation technique, three-dimensional surface can be extracted. Triangulation technique is shown here. By altering the height of the sample, the laser line is projected to another position on the detector. As you can see here on the C image, the surface is not complete. This is due to the parallax between camera and laser. In our study, we use distance and curvature correction. Distance correction is used because the inverse square law states that the irradiance from the isotropic point source varies inversely with the square of the source distance. We measured white standard on various object-to-camera distances and fitted the data in every separate pixel with quadratic polynomial. The corrected intensity was calculated based on the height of the sample for every pixel of hyperspectral image. As you can see on the image here, the irradiance on the surface depends on the angle between incident light and the surface normal. In the end, we would like the result to be as the sample would be illuminated from the perpendicular direction to the surface, as is for this case here. This is why we use curvature correction. Firstly, surface normals are calculated from three-dimensional profile of the sample. Then the inclination angle is calculated and used in Lambert cosine law, which is written right here. This is how we get our corrected intensity. So let me present you the results. As I said before, the curvature artifact effect is present as lower signal in sample regions with larger camera to surface distance and higher inclination. The correction method was used on three different samples: spherical object, Lego figure, and in vivo human finger. On spherical object, we can see that intensity over the surface became more homogeneous. You can see it right here. If we look at the plot below these images, this plot, the black dashed line is indicating how our intensity profile would look if it was ideal. Our corrected intensity profile gets quite similar to the ideal one, to the red one right here. On Lego figure, the results are a little bit less perfect. We can also notice some increase of image intensity on some part of images, which are here in these red circles. This is due to inter-object reflections between opposite surfaces. If we look at the last result, which is in vivo human finger, we can see on these images here and on these images here that the intensity over the finger became more homogeneous. We can also see how the correction affect reflectance spectra on the curved part of the human finger. So for a conclusion, I would say that the method substantially reduced sample surface shape and samples to camera height variation artifacts. Results of this study makes further analysis of spectral images more accurate and increases suitable area for analysis. The correction procedure can be applied to diffuse surfaces imaged by any spectral, monochromatic, and hyperspectral imaging system if 3D information is available. So that would be all from my side. I would like to thank everybody for listening and have a good day.